is whether you can see me now.
We can see the presentation, yes.
But not my face.
No, that's not you.
It's much better.
Because I like to hand wave a lot. But okay, anyway, let's go. Well, Massimo told me they have 2 hours, right?
Yes.
Okay, let's focus, people. Sorry for not being there, but well, a lot of things have happened. But anyway, I'm going to tell you today a story about monochromatic and oh, that's wrong. Oligochromatic extreme mass resonance spirals. Yeah, this is something that I have been working on this summer. So you know this story, right? I don't have to go through this list. Extreme mass resonance spirals, you have something branching to 10 to the 4, 10 to the 6, supermassive black hole, and this range of masses corresponds to relaxed nuclei, which is a very good luck, because this is again something that I've been saying since I was like 11 years old. But with Lisa, it is by chance that this corresponds to relaxed nuclei. I don't think that anybody took the time to check whether these galactic nuclei are relaxed or not. They are relaxed, and this is good news, because you expect to have stellar mass black holes close to the supermassive black hole. With Lisa being extremely optimistic, you can see these things out of redshift of 4, like in the paper by Babak et al. And being pessimistic, I would say, out to redshift of 1. But in any case, the rates for a Milky Way-like galaxy are very low, 10 to the -5 and 10 to the -6 per year. But this is what I want to talk about today. So these rates correspond to the stellar mass black hole or compact object. I'm going to just assume that they are just stellar mass black holes. These rates means that so the small compact object is crossing the event horizon every 10 to the 5 years, 10 to the 6 years, which means that if you look at the galactic center, the probability that you get a 1 doing that when Lisa's flying is, well, 5 years mission duration, 10 years, say, divided by 10 to the 6, which is nothing. Well, you can take into account this thing that we did in 2013 about how the last stable orbit moves to the left or to the right, and that helps a little bit with the event rates, but not a dramatic change, right? But in any case, you do not expect to have extreme mass resonance spirals at the galactic center, right? Well, not really. But that depends on what I said before. That depends on your definition of what is an extreme mass resonance spiral. So I am sorry, but I feel the obligation of introducing some taxonomy here now. So the evolution of an extreme mass resonance spiral can be divided into 3 stages. The monochromatic EMRIs. This is just about, these are boring extreme mass resonance spirals. They are just not moving at all in frequency. It's like these wide of binaries, right? They're just going like a for 10 years of the mission duration. And they are very far away from each other, 10 to 5 years, something like that, which is why we can consider them to be mono, because we don't live 10 to the 5 years. We die after 80 years, 90 years, in my case, 120. Hope. Then we have now yes, with a Y, oligochromatic EMRIs. Oligo is an affix, to be more precise, is a prefix. That means a few beams of frequency. This is a more advanced stage in the evolution. We're looking at about 10 to the 3, 1,000 or 10,000 years from merger. And they will cover a very short frequency range. And then we have the polychromatic extreme mass resonance spirals. Poly meaning a lot, right? And using Bernard Schutz's words, these are the ones we have been talking about all along. Okay, so number 3 is are the extreme mass resonance spirals we have been focusing on. Okay, so Humami, let's assume that we fly LISA today and we look at the galactic center, and by whatever reason, because Allah, God, or Buddha placed an extreme mass ratio at the galactic center. So how would that look like? I don't know whether you can see my cursor, but anyway, we'll read it.
Yes.
Okay, wonderful. Look, this is infinity. Okay, so this is the synchronous ratio for a 1-year observation, meaning that if 10 to the 4 years before the plunge, you get to observe the system for 1 year, you would get a synchronous ratio of, well, getting close to 2000, right? And this is simply because the source is very close to us, 8 kiloparsecs. This n tilde here, sorry about that, this is some stupid notation. It means 10 solar masses. Now, I have a decomposition here in harmonics to the different contributions. So for for the contribution to the synchronous ratio of each of the harmonics. Now, for instance, look at this point here. If you go up, here you see, I don't know whether you can see that, delta S, this is the error in the extraction of the spin parameter that you would be making if you had one of the things, and it's 10 to the minus 5. Delta M O dot, or whatever that symbol is, yes, is the error you would be making estimating the mass of Sagittarius A star. It is 0.07. And this is, well, the time, 4,000 years before the plunge. I cut this study at 10 years before plunge because, well, I just removed the observational time. By the way, look at these numbers. 10 years before the plunge, you get 10 to the minus 11 in the parameter extraction of the spin. But of course, the closer and closer and closer you get to the right, the less and less likely it is that you have one of these things here, right? This work about parameter extraction and etc. was done by a Chinese student, Yiren, because I cannot do these things. And she was using waveform Salabarak and Katla. Okay. Well, if just for fun, if you have a black hole, stellar mass black hole with a mass of 40, then the numbers look also very interesting. And this corresponds to 500,000 years before plunge. Okay, and this is starting over here with a synchronous ratio of 10. Okay, very nice. So now this is interesting, but what about event rate? Well, Massimo told me I have 2 hours, but it looks like I have only half an hour, so I have to speed up. This is basically, and I don't want to bore you, but this is basically almost a copy and paste from the calculation that I did in 2019. When I was talking about, extremely large mass resonance spirals. But the calculation in this case is easier because relaxation is provided by stellar mass black holes, and I am interested in one species, which are stellar mass black holes. I'm not looking at brown dwarfs or main sequence stars or anything like that. So you just have to integrate in phase space the number of objects that you have at a given symmetry axis on a given time scale, which of course is the relaxation time, and that is also depends on the distance to the supermassive black hole. And of course, not all of the phase space contributes. It's only the loss con, and you've been talking about loss con today a lot. Okay, I will just very quickly just flash you the slides. Loss con can be approximated. Tal did that with Vivian 2001, so that you get what you need. I can slow down or come back later if you want, but I am more interested not in these results, but in what I have to tell you later. You assume a power law distribution, like Peebles, 1972, right? You differentiate, so we have the numerator that you need for the integral, which is the number of black holes as a function of the radius. Now, it is interesting to have the relaxation time as a function of the radius, because it can change quite a lot depending on where you are. You are very close to the supermassive black hole, you are very far away from it. So, as I said before, relaxation, you can prove actually, and that's proven in the 2019 paper, that relaxation is given, is due to the most massive stellar species, mass black holes. And you normalize, you get this T naught, which looks horrible. Now, you know this thing, right? So you equate the relaxation time at percent to the gravitational wave time scale, and that gives you threshold plus. This is coming from the paper in 2007 that I wrote with some people in the room. Actually, Cole is there, I believe. And this function over here, you have heard about this also. This is taking into account the asymmetry between pro and retrograde orbits. We look at the elastic orbit. Anyway, so the interesting thing is that in this calculation, everything is self-consistent. So in this definition for the critical radius, just to give you an illustration of what it is. So this is an axis. This is the 1 minus the eccentricity. This line over here is the last stable orbit. And this red line here is giving you the threshold between dynamics, which is going to be above the red line, and general relativity, which is going to be below the line, right? So in the conjunction of the red line with the last stable orbit, you derive the critical radius. And this expression is giving you that position for any given configuration, for any gamma, any, well, I will define what is a naught for any mass of the black hole and mass of the stellar mass black hole. So that's an advantage. The integral that I was showing you before can be solved analytically if you do not trust the computer algebra systems, because I tried to solve the integral with one of them, and the result was very long and horrible. It looks like this. It looks very complicated. It is not complicated. But yeah, you can see already the numbers, right? You have here 10 to the minus 6, blah, blah, blah. These are just, these still the things are dimensionless. And here you have 10 to the minus 6, 10 to the minus 1, multiplying, blah, 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 blah. And then you have this function, which is giving you the position of the last stable orbit. And this contribution here, basically, well, I just add this one over here, sorry. I just added it for completion, because the contribution is basically 0. So, yeah, well, this lambda tilde is Coulomb logarithm normalized, and naught tilde is the number of black holes providing relaxation, R naught tilde is the influence radius, and the N tilde is the mass of the black hole. So the advantage is that that expression contains all physical information, including the relaxation time and critical radius embedded in it. Okay, anyway, I have to speed up. So this is the event rate at the galactic center. So number of objects crossing the event horizon for a stellar mass black hole of mass of 10 as a function of the spin, the inclination of the orbit. So you see that here we have a 10 to minus 6, and here we have 10 to minus 5. The difference is in the influence radius. So if you look at the galactic center, it looks like we're over here. Okay, the influence radius is about 3 parsecs. So that these should be the rates, 10 to minus 6. Now, the values for the other example that I was taking, 40, are somewhat larger, but they're still low. Okay, so you might be asking yourself this so much faster. We knew this already. We have been knowing this for a very long time. But this is the point. I was mentioning to you this before. This is electrons ratio. So you've got this thing in band 500,000 years before the plunge. These early inspiral stream maceration spirals are going to be on band with a synchrotron ratio less than 10, 500,000 years before the plunge. Again, EREN calculated the synchrotron ratio here without any approximation. This is just the inner product of the waveforms. So, as you say in English, time is of the essence. So the point is that the early stages, so this monochromatic and oligochromatic stream maceration spirals, are going to spend a long time on band. So you have lifetimes of 10 to the 5 years, an event rate, say of 10 to minus 6 years, but how many of these are in band? Well, the point is that, let me just flash you this. So you have a line density, which is giving you, so G is the number of sources that you have within a delta of symmetry axis, right? Oops. You know what is the influx of stars over here. This is the critical, I don't know why I'm calling this max now, but anyway, this is the critical radius. So you have an influx of things here. And so this represents the threshold between dynamics and relativity, right? But not all of these sources will make it to the band. So you have here a condition, which is a symmetry axis, which corresponds to the symmetry axis that these sources should have when they are in band of Lierse. Okay, so not all of these sources will make it here. When they get here in at this zone number 2, they are quite eccentric and not that loud. And when I mean not that loud, means synchrotron ratios between hundreds and 10 to the 3 or something like that. And then you have a break radius. This is the transition from being very eccentric to be very circular. And I am actually approximating the number so that here I am assuming that the eccentricity is 1. And here the eccentricity is 0. That helps to do the things analytically. And you have a minimum radius, right? Because then the things plunge with a supermassive black hole. So you can normalize, you get your normalization factors, and therefore you can solve the differential equation for the line density. And the number of objects, so these are the normalization conditions. It is easy, actually, to derive it. And it looks like this. So the number of objects which are very eccentric will be, so is R, sorry, this event rate, so your sinking condition, times the time spent in band, times this weighting function omega-1. The same for N2 and N3. These expressions are ugly, but easy to solve. And these are the results. So this is the total number of EMRIs, so early stage stream maceration spirals, assuming a mass of 10 at any given time, because what I was showing is a statistical, so it's a steady state solution, which means that if you go back 500,000 years in the past, these are the results. If you go 500,000 years in the future, these are the results. So in N1, so the extremely loud and eccentric things are basically negligible, 10 to minus 3 over here. Now, this is for an influence radius of 3, for influence radius of 1, things are a little bit better, but not that better. If you go to an influence, to N2, so they are eccentric, but not that loud. So you get, say, 10 to minus 1, something like that. And for influence radius of 1, you are, well, in the range of 1, say. Now, if you change the mass, so if your black hole doesn't have a mass of 1, but a mass of, 10, but a mass of 40, then things change. Even for a realistic influence radius of 3 parsecs, at the region 2, so very centric, not that loud, meaning thousands of synchronous ratio, you get tens of them, depending on the inclination and spin. And the extremely loud ones, because these things are reaching almost 1 million in synchronous ratio, well, this is of about, say, 1. Now, what does this mean? This means the following. So you have a fore and a background population. Being extremely naive, you could think the following. I'm going to plot randomly. This is in the quadrupole approximation, by the way. This is not Barak and Cutler. This is just one order below that. This is how I kind of, I don't want to call it a confusion noise, because this is not noise. These are extremely interesting sources. But if you just let, vary these symmetry axis between a range of astrophysically relevant values, the eccentricities and the distances, this is how it would look like. So it looks like we're covering this part of the sensitivity window of LISA. And again, these sources, if we're looking at the galactic center, they have extreme synchronous ratios. Now, because the synchronous ratio is inversely proportional to the distance, we can rescale the results from CQSJ star. In the case of a 10 solar mass black hole, it looks like this. So we can go out to, say, 10 to the 5 kiloparsecs, which is 0.1 gigaparsecs, right? But this is a naive picture. This is a naive picture. This is you would actually be making a mistake because the real contribution must be different. So if you want to, this is like calculating the binary wide dwarf background or foreground for the LISA curve. So you have to estimate the total strain. The combined amplitude is going to be an incoherent sum, but it's not just that. It's not just an incoherent sum. It's an incoherent sum and weight or pondered by different weights, xi. This weight, xi, represents the occupation fraction probability, because as you progress in frequencies towards the merger, the evolution is going to be faster and faster. Remember that in the quadrupole approximation, the time scale for gravitational waves is proportional to the symmetry axis to the power of 4. So the closer and closer and closer and closer and closer you are to the merger, the faster and faster it will evolve. And it is more and more unlikely that the object is going to be found at the later stages. So but the point is that even if one particular source is not in band, the addition or multiplication, because multiplication is essentially an addition, of that particular population fraction might be. I don't know whether you understand what I'm saying, but this is a little bit like Cosmas in the Copleuster's paradox or Olber's paradox, if you allow me the silly or maybe even stupid comparison. So you have, it's not that if you consider one single source, which is very faint and very far away from you, of course you are not going to hear that. You're not going to observe that. But if you have a lot of them, they will contribute by adding up. And that adding up will very likely contribute to this foreground noise in the band. Even if one individual source is not going to be able to make it to the sensitivity window, the summing up of this incoherent sum of different sources will very likely make it. But just to go back to that paradox, the interesting thing, of course, as you know, in gravitational waves, we're not measuring energy, we're not counting photons. So this is not decaying as 1 over r square, because we're capturing the full wave. So we can get to much, much further distances. So this forest, as I call it, must extend beyond those 0.1 gigaparsecs. Now, so how does the fore and background look like? This is the most important question, right? And the answer is, I don't know yet, because I have not had time to do it, but I am doing it not as we speak, because I cannot do 2 things at the same time, but I am working on it these days. So, in any case, these early inspiral stream mass spirals can be divided, so EMRIs in general can be divided into 3 categories: monochromatic, and again, that's wrong, why? Oligochromatic, which are the things that they call early inspiral simulation spirals. The polychromatic ones, the usual ones. If we consider the galactic center, then we can map these categories with a Singleton ratio, meaning that the monochromatic sources have Singleton ratios between 100 and 1,000. Oligo, again, wrong. With Singleton ratios between 10 to the 3 and 10 to the 5. And for mono and oligo stream associations, but it's not the rate that matters. It is the rate and the time spent on band being detectable, plus their cosmological, I don't know how to say this, number. Because they have large Singleton ratios, and so EMRIs must adapt to create a fore and background signal. And this forest will cause trouble up to, say, 10 to the minus 2 hertz. Because of the huge Singleton ratios. What is the shape of the forest? I am working on it. And now I would like to show you something different, a video. I think I can play it here, Massimo, because I told Massimo that I would not be able, but I am. Wait a second.
Wait a second.
No, I can do it. I can do it. Don't worry.
Okay.
Believe me. Have faith. Okay. Let me go back. Okay. So I have this is just to play because I wanted to play a little bit. I convinced a very well-known musician here in Berlin. I am in Berlin right now. To do this silly exercise with me. Don't worry, because the video is 1 minute. And again, my goodness, this whole ego with anyway. So I don't know how loud is the volume. Watch out, Matteo. I don't want to kill anyone. But Marta Massini is playing with a flute these different things, so that you can have at least an idea of what is going on. You should hear sound. If you don't, let me know. So first of all, let's have a look at the musician. Matteo, did you hear that?
Yes.
Okay. Now let's go for monochromatic stream association spirals. So this is how they will feel like. Different sources, separate sources, of course. Oligo, again with the typo. So So you hear the frequency is going up, but it's not going to keep. It's just you know, just scanning a few beams in frequency. Then now two sources together, mono and or oligo. And now the full thing. So this is what I'm trying to work out now. This is the total contribution. Some of them will be very loud, some will be very, you know, dim, and you will have some of them being completely monochromatic, and some of them will be evolving a little bit. But it's going to be. I think that about the numbers, I had hundreds of them. Okay. And that's it.
Thanks a lot, Pau. We have a question from Kurt.
Hey, Pau. Sorry you couldn't be here. So thank you for the auditory experience. I wish I meant you were talking, not the music at the end. In any case, I have sort of in the spirit of discussion, I'd like to first understand if I have properly understood what you're saying, and then I wanted to challenge it. So I think what you are saying is that because you have a lot of cases in which you have stellar mass objects spiraling around supermassive black holes, that they're going to be dipping into the frequency range of LISA over and over again, and this is going to provide foreground or background. I think your overall concern is that this might provide, in fact, a confusion background or foreground, depending on how you define it. But I guess, first of all, did I understand that correctly?
Probably, but you have to work on your Spanish accent. Can you make it stronger, please?
So you're worried that this is going to provide a background or foreground that could be confusion?
I'm not worried, but I think that's going to be the case.
Okay. So one of the things you mentioned is that with Olber's paradox, or for something you've for some reason called Cosmas Indicopleistes paradox, that is 1 over r squared, and this is not. But the thing is that if you're going to have confusion, you need to have more than one source per frequency band, about 10 to the minus 8 hertz.
Yeah.
These are not going to have phases that line up with each other. My guess is that ultimately you are going to have something more like 1 over r squared, so it's not going to be any different.
Probably. The honest answer is that I don't know, because I am doing it right now. But yes, I have also thought about that. I don't know. I have to do the calculation.
And if this is true, then we may have a situation in which, like with Olber's paradox, even if you eliminate the sun, the galaxy dominates the optical signal. You may have a similar situation for these signals. So it could be ultimately that we have the positive situation that, as has also been suggested by people like Kelly Holly Bockelman, that the frequent, very high eccentricity events in the LISA band from our galactic center will provide us a signal without obscuring the rest of the universe.
But the last part I didn't understand very well, but I agree with you. But the point is that I don't know, and this is why I say I don't know yet. But as soon as I have the draft, of course, I will. Actually, there's something that I wanted to ask you, because so yeah, as soon as I have the draft, I would like to circulate it among all of you and get some feedback from you.
Thank you.
Well, there's a follow-up actually about the Olber's paradox thing. You might be interested in a series of papers by Bruce Allen. He did, he got somehow interested in pulsar timing arrays recently, and in the behavior of the helix and Downs correlation. And he did some calculation about that, making a model of the signal exactly using the same, the same approximation based on Olber's paradox. So, and well, essentially modeling the signal as concentric the sources as concentric shells. And the argument is is exactly what Cole was saying, right? Because since the addition is incoherent, that's the same situation. So, but you might want to have a look at that because it uses the same Olber's paradox formalism to that.
Okay, that's fun that he also thought about that.
Yeah, it's they came out in the last 3 months, and he's the first author. So if you just look for it on ABS, you find it easily.
Thank you, Alberto.
Nice to see you again, Pau. Sorry I couldn't be in person. If we take the astrophysically optimistic, but maybe Lisa pessimistic hypothesis that the center of our Milky Way really is a crazy place and there are just huge numbers of brown dwarfs and compact objects flying by Sagittarius star all the time, providing a really powerful foreground signal. Is this something that can be sort of subtracted off or compensated for in some way in LISA data analysis because we know the location with very high precision?
Well, I think it depends on how well you can do your waveforms, right? But it should not be a big problem because they are so loud and they are basically not moving in frequency that they should not be a problem. The people have been playing with this, they have been working hard for this, do you remember this mock LISA data challenges? And people like Niels, right? Cornish, right? He managed to remove thousands, if not 10,000s of Waldorf binaries at once. So I don't see why this would be a problem. But it's going to be a little pain. But on the other hand, you are going to be able to obtain information about the spin without any redshift, of course, with ridiculous error and the mass of the supermassive black hole. In any case, this is something to think about because I think that it stands to reason that these things are going to be there.
Wouldn't we be okay unless we had at least tens of thousands of such objects in that frequency band? Because if you've got 10 to the minus 8 hertz frequency resolution at 10 to the minus 2 hertz, that's 1 million bins. So unless you've got something approaching that number of bins, most bins will not have a source. So I think I wonder whether that would mean that even if you have that many, it's not going to obscure most of the frequency range.
Yeah, that makes sense.
Centers this one, or the right wing.
Yeah, that's the last one of the 3. Yeah, there should be 2 others with Bruce Allen sole author of those, which gives more insights in the whole calculation. One is a sort of application of the results to specific pulsar timing arrays.
I see. But the one complication that I have is that, as I said, the probability that you find the source in this spin of frequency or that spin of frequency is different, and I have to ponder that probability and include that into the calculations.
Okay. Do we have any other questions for Paul?
I have a lot.
Oh, you do.
So how are you doing in Como?
So far, so good.
Yeah. We only lack you.
I don't miss you, Cole. Sorry. I'm joking. I love you. Okay. So that's all I have to tell you. Did you like the movie?
Awesome.
Very nice. Okay. I can sing something if you want.
But let's thank Pau again. We are even on time, which is surprising for me. But yeah, we did a good job. So we reconvene at 2 p.m. European time with Odelia.
What is European time? The Canary Islands and Europe.
So,
Portugal.
Central European time.
Your time, wow, you're
Your
leader,
time.
right?
Okay. Bye, people.
Bye.
Your time.
Can you recommend where we should go for?
Well, I think we have someone who's way more expert than